Welcome back. I hope you had a chance to watch my previous videos on motion under gravity. In this video, I'll walk you through a few examples that will help deepen your understanding. I hope you find it useful. In this first example, we will analyze the motion of a ball projected from a point 10 meters away from a 5 meters tall tower. The ball just manages to clear the top of the tower. Our task is to derive the expression displayed on the screen for the trajectory of the ball. Here, theta represents the angle of projection, u represents the ball's initial velocity, and g denotes the gravitational acceleration. We will set the origin at the point where the ball is thrown and define the initial velocity components as u cosine theta in the horizontal direction and u sine theta in the vertical direction. The horizontal velocity remains constant since no force acts in that direction. This means the ball's horizontal speed remains unchanged, even after traveling 10 meters. Given that we know both the horizontal velocity and the distance to the tower, we can determine the time taken for the ball to reach the tower. The time taken to reach the tower is found by dividing the horizontal distance by the horizontal velocity. Next, we will derive an expression for the vertical displacement of the ball. Since we have defined the origin at the point of projection, the initial vertical displacement is 0. The initial vertical velocity is u sine theta, while the gravitational acceleration g acts in the downward direction. Since gravity opposes the initial upward motion, we include it as a negative term in our equation. The ball reaches a height of 5 meters after a time t, which we determined using the horizontal motion of the ball. By substituting all known values, we arrive at the following expression. Our next step is to simplify this equation systematically, using algebraic manipulations and trigonometric identities where necessary, to arrive at the final form of the desired expression. Alright, let's move on to the next part of the question. Given that the angle of projection theta is 45 degrees, we can now determine the initial velocity of the ball by substituting this value into the derived equation and solving for u. Step by step, we can simplify the expression to find the initial velocity of the ball. We take gravitational acceleration as 9.8 meters per second squared and disregard the negative value. After a few steps of simplification, we determine the initial velocity of the ball to be 14 meters per second. Now, to determine the velocity of the ball when it reaches a height of 5 meters, we can apply the principle of conservation of energy. This states that the total mechanical energy comprising kinetic and potential energy remains constant throughout the motion. At the point of projection, the ball has only kinetic energy, since we take the reference point at the launch position, making its initial potential energy 0. At a height of 5 meters, the ball has both kinetic and potential energy. By equating the total energy at both points, we can solve for the velocity of the ball at this height. After applying the conservation of energy and simplifying the expression, we determine that the velocity of the ball as it clears the tower is 9.9 meters per second. Let's move on to the next example. A ball is thrown from a height of 2 meters with an initial velocity of p in the horizontal direction and q in the vertical direction. It takes 4 seconds for the ball to reach the ground, landing 50 meters away from the tower. Our goal is to determine the initial velocity of the ball and the angle of projection. Additionally, we need to find the duration for which the ball stays above a height of 5 meters from the ground. We first need to define a reference plane. It is convenient to take the base of the tower, from where the ball is projected, as the reference point. This is because later, when calculating the duration for which the ball remains above 5 meters, the measurement will be taken from ground level. However, the choice of reference point depends on individual preference and convenience. We can determine the horizontal component of the velocity, p, by dividing the horizontal displacement by the total flight time. This calculation gives p as 12.5 meters per second. To determine the value of q, we can use the displacement equation for vertical motion. The ball reaches the ground after 4 seconds, meaning its final displacement is 0. However, since it is projected from a tower of height 2 meters, the initial displacement is 2 meters. The initial velocity in the vertical direction is q, which we need to determine. The gravitational acceleration acts downward, making it negative in our equation. For simplicity, we take it as 10 meters per second squared. Since the ball travels for 4 seconds, we substitute t equals 4 seconds into our equation. By solving this equation, we can determine the value of q. Which comes out to be 19.5 meters per second. To determine the magnitude of the velocity vector, we take the square root of the sum of the squares of its horizontal and vertical components, p and q, respectively. So, the ball's initial velocity works out to be 23.16 meters per second. Next, we need to calculate the angle at which the ball was projected with respect to the horizontal. The ratio of the vertical velocity to the horizontal velocity gives the tangent of the angle of projection relative to the horizontal. This results in an angle of projection of 58 degrees. All right, let's now determine how long the ball stays above a height of 5 meters from the ground. Essentially, we need to find the time interval during which the ball remains at or above this height as it moves along its trajectory. To do this, we start by calculating the time it takes for the ball to reach 5 meters, using the displacement equation. Since this equation is quadratic in time, solving it gives 2 possible values. The first value represents the moment the ball reaches 5 meters while ascending, and the second value corresponds to when it returns to the same height while descending. The duration for which the ball remains above 5 meters is simply the difference between these 2 time values. This tells us how long the ball stays at a height greater than 5 meters before falling below it again. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. This next example presents a fascinating challenge that deepens our understanding of projectile motion. It examines the trajectory of a projectile within a confined space, considering perfectly elastic collisions and the relationship between horizontal and vertical motion. So, let's dive into the problem and break it down step by step. In this scenario, a ball is projected from a hole at the center of a cubic room with side length 2L at an angle alpha to the horizontal. As the ball moves, it undergoes 3 perfectly elastic collisions with the walls before exiting through the same hole after a total time t. Our goal is to derive an expression for the initial velocity in terms of alpha and t. Additionally, we will determine the minimum initial velocity required to ensure that the ball exits the room before reaching the highest point in its trajectory. Since the collisions are perfectly elastic, the ball retains its energy throughout its motion. Looking at its horizontal movement, the ball first travels 2L to the right, then 2L to the left, covering a total distance of 4L before exiting the room after a total time t. Because there is no loss of kinetic energy in the horizontal direction, its horizontal velocity remains constant. By dividing the total horizontal distance by the time taken, we can determine the horizontal component of the ball's velocity. From this, we derive an expression for the initial velocity of the ball in terms of t, alpha, and L. All right, let's move on to the next part of the question. Here, we need to determine the minimum velocity required to ensure that the ball does not reach its maximum height during the time period t. To do this, we first need to find the time at which the ball reaches its maximum height. Since the vertical motion follows a parabolic trajectory, the time to reach the peak can be found using the displacement equation in the vertical direction. Let's substitute the initial conditions and rearrange the displacement equation to solve for the time at which the ball reaches its maximum height. By setting this term to 0 and solving for time, we can determine when the ball reaches its highest point. Now, for the ball to remain in motion without reaching its peak displacement, the time taken to reach the maximum height must be greater than or equal to half of the total time t. This condition ensures that the ball exits the room before completing the upward phase of its motion. By substituting the previously derived expressions for t sub p, the time to reach maximum height, and t, the total time inside the room, we can determine the minimum initial velocity required to ensure that the ball does not reach its maximum height while still inside the room. This ensures that the ball exits the room before completing the upward phase of its motion, preventing it from reaching the peak of its trajectory. That brings us to the end of this video. I hope you picked up some fresh insights into projectile motion, perhaps a perspective you hadn't considered before. More importantly, I hope you found it both informative and practical. If you haven't subscribed yet, I'd really appreciate your support. Just hit that subscribe button. And don't forget to like this video and share it with others who might find it useful. I'd love to hear your thoughts, so drop a comment below. Until we meet again in another video, take care and goodbye.